So a chemical equation is balanced when there are equal number of atoms and charges on both sides of the equation. Okay, so now let's see another example. I'm going to put an example involving charge. Okay, so I will put on the screen here. Okay, let's say an ionic equations in this way. Let's say I create zinc 2+ react with, let's say, okay, zinc atom. Okay, zinc atoms react with, let's say, silver ions. This is where they form zinc 2+ plus silver atom. Okay, so this is the equations. Now, if you look at this, you will feel like, is it balanced or not? One zinc on the left and one zinc on the right. Okay, so seems to be, it has the same number of atoms for zinc, one silver on the left and one silver on the right. So it seems like it's balanced also. But if we look at the charge, so you see the charge here on the left-hand side. So left-hand side is all the way here. The charge here is +1. So the charge here is now +2 on the right, +2. So the charge is not balanced, even though the atoms are balanced. So in that case, we need to multiply with 2 on the left. Okay, so multiply with 2 so that we get +2 at the end. So when you multiply with 2, so basically you need to multiply 2 to the one that contribute the charge. So you have to multiply 2 for this silver so that the charge become 2+. Okay, so when you multiply 2 to the silver ion, so you have to multiply 2 over here as well. Okay, you have to multiply 2 also, so that the number of atoms are the same. So 2 silver on the left and 2 silver on the right. In terms of charge, 2+ on the left and 2+ on the right. So in that case, we balance the equation. So where we have the equal number of atoms, one silver and one silver 2+ on the right, that is same number of atoms, and one zinc and one zinc 2+ just now, and now 2 silver ions and 2 silver atoms. So in terms of the number, it is the same. In terms of charges, it is balanced also. You see +2 and +2. So we managed to balance the element instead of saying atoms, which is not that accurate because this is atom, this is ion. So the element or the substance are same in number. Silver, same in numbers. The charge is also same. Now we put the state symbol.
So, I don't seem to understand it. Can you repeat again?
You want to balance the equation, right? You have to balance the number of.
We are balancing the power or the atom, the number of atoms.
Yep, the atoms, and then we have to balance the charge.
Okay.
Yeah, so you see one zinc and one zinc balance. Okay, so 2 silver and 2 silver balance. How about the charge? 2 times +1, +2. +2. Okay, the charge is also balanced. So you have to balance both the charges as well as the atoms on both sides of the equations. So that's why we put 2 over here and here to balance the number of atoms as well as the charge. So that is what we need to do here. Okay, so this is one example. Of course, you have more examples. Okay. Most students, they can easily balance the atoms, but they forget about the charge. Okay, they forget about to balance the charge. So that is the problem. Okay, so now we look at the next point, state symbols. So S stands for solid, L stands for liquid, G stands for gas, AQ stands for aqueous solution. So for example, this is zinc, right? Zinc atom is a solid. So we put S here. Silver ions, once they become ions, they are normally aqueous. So this is aqueous. So zinc 2 plus, this is ion. So ion is normally in aqueous. Okay, and then silver is solid. So atoms in solid. So that is how we put the state symbols. So we put state symbol if the question asks you to do so. If the question never asks anything, no need to put state symbol. Okay, so let's see. Okay, so let's say I put one more example. Okay, I put one more example since you need time to process all this, right? So I put one example here. Okay, let's say I have iron react with copper, and let's say iron become iron 3 plus. The copper become copper atom. Okay, so for this case, how are we going to balance the atoms as well as the charges? So first, when you look at the atoms, right, it seems to be like balanced already. One Fe on the left, one Fe on the right, balance. Cu2 plus. Okay, we have one Cu on the left, one Cu on the right. It seems like it is balanced. But the thing is, the atoms seems to be balanced, but the charge is not. If you look at left-hand side, we have positive 2 on the left. But if you see the right-hand side, we have positive 3 on the right. So it is not balanced yet. Okay, so we need to make it balanced. So we multiply 3 for this in order to get positive 6. We multiply 2 for this in order to get positive 6 so that it balanced. So if you multiply 3 to the charge here, so of course you have to do something like this. Multiply 3 to the copper. Multiply 3 to the copper so that the charge become positive 6. So if you multiply 3 to the copper, you have to multiply 3 on this side also to balance the atom. So you have to multiply 2 to the charge, the ion with positive 3, which is this one. So Fe3 plus, you have to multiply 2. So if you multiply 2 here, then 2 iron. So here you have to balance it with 2 iron. Okay, so now after you balance it, now you check again. First, we have 2 iron on the left, 2 iron on the right. We have 3 copper on the left, 3 copper on the right. So in terms of the number of atoms, it is balanced. In terms of charges, 3 times 2 plus is 6. 2 times 3 plus is 6. So in terms of charges, it is also balanced. So this is how we balance the equation. And again, if you want to put the state symbol, so this one you can put solid. This one you can put aqueous. And then aqueous. And then this one solid. So this is the example on how we balance the equation. Okay, now let's continue with this part. So what we have here is the Valency table. The Valency table. So which are the charge basically. Okay, so nitrate. The formula is NO3. The charge is negative. So valency is 1. So you will see the valency is just equal to the charge. Okay, so hydroxide OH minus, minus means minus 1. So that's why this is 1. acetate or ethanoate, CH3COO minus, the charge is -1, so valency 1. Carbonate, CO3 2 minus, I had to memorize the formula, CO3 2 minus, the charge is 2 minus, so the valency is 2. Sulfate, SO4 2 minus, the charge is 2 minus, so the valency is 2. So it's related to the charge. Silicate, SiO3 2 minus, so the valency is related to the charge again, which is 2. Phosphate, PO4 3 minus, the charge is 3 minus, so the valency is 3. Okay, so that is the formula. Valency is not so important, but the charge.
Okay. So like, is it possible if they ask questions regarding valency in exam?
Yes, actually, but
then
very
if
rare.
So if like they, for nitrate it's negative, so actually we shouldn't put -1 now for as an answer.
Yeah, we just put the something like the magnitude only.
Oh,
No need plus minus.
Okay.
Okay, so that is the valency. Okay, now we look at the ending of names. Compound ending with IDE only contain 2 different elements. Okay, compound ending with IDE only contain 2 different elements. So I give you one example. Okay, let's say compound carbon dioxide. You know carbon dioxide, CO2. Okay, so IDE is here. 2 elements, 1 carbon, 2 oxygen, 2 types of elements. Okay? 2 types of elements, carbon and oxygen. So carbon dioxide. And let's say another example, sulfur trioxide. Okay, so the name has IDE also. So SO3. So also two types of elements, oxygen. So compound with IDE. Compare with another one. Let's say element with IDE. Element ending with IDE. Ending with IDE. Okay, let's say oxide. Oxide. O2 minus. Sulfide. Okay, let's say S2 minus. So you realize different idea. So elements ending with IDE, they are negatively charged ion. Okay, negatively charged ion. But compound ending with IDE, there are 2 different elements that form the compounds. Okay, then let's see. Compound ending with ATE contain oxygen. Okay, so let's say sulfate. Sulfate. Okay, you see the ATE there, sulfate ion. Yeah, so SO4 2 minus. The ATE refer to the oxygen there. So let's say nitrate ion. So you can see the word ATE at the back. So it refers to the presence of oxygen. NO3 minus. So the oxygen is there. Okay, so you can see the example in that way. Okay, now let's see the next point, the next subtopics here. Masses. Relative atomic mass, AR. Mass of one atom of an element. Okay, so of course, mass of one atom of an element. For this, you can always look at the periodic table to find the relative atomic mass. So it shows the relative atomic mass. Okay. Relative to 1/12 of the mass of one atoms of carbon-12. So this is the definition for relative atomic mass. It's the mass of one atom, which is not in kg, but it is in relative to 1/12 of the mass of one atoms of carbon-12. So they compare with carbon-12. Okay. But it is not comparing straight away. It's compared to 1/12 of the mass of carbon-12. Okay, so that's the definitions. Okay, now let's say, for example, you will see hydrogens. So the relative, okay, I put AR. So the AR is equal to 1. Okay, so that means hydrogen atoms has the same mass with 1/12 of the mass of one atoms of carbon-12. So let's say helium. Helium, if you check the periodic table, you will get relative atomic mass as 4. As 4. So that means helium, the relative atomic mass is 4 times compared to 1/12 of the mass of one atoms of carbon-12. 4 times heavier than 1/12 of the mass of one atom of carbon-12. So it's something like that. Okay, so we don't put the relative atomic mass in kg. It's just number without unit, showing that it is comparing the mass with 1/12 of the mass of the carbon-12. Okay, so we see the next point. Relative molecular mass, sum of relative atomic masses of all the atoms in one molecule of the compound. So let's say example. So I put down here. Okay, so for example, if I have carbon dioxide, so carbon dioxide. So to find out the relative molecular mass, so you have to add up the relative atomic mass of the carbon and the relative atomic mass of the oxygens. So you look at the periodic table, you will realize that carbon, so of course in the periodic table you will see something like this. So that will show carbon as 12, 6, and then oxygen as 16, 8. You will see something like that. Okay, then the relative atomic mass is the number which is greater in value. So the 12 and the 16. Okay, now you want to find out the relative molecular mass. 1 carbon is 12, 2 oxygen is 2 times 16. Okay, then you get 44. So the relative molecular mass for carbon dioxide is hence 44. Okay, now we look at the next point, the mole concept. Okay, the first point, a mole of a substance is the amount that contains the same number of units as the number of carbon atoms in 12 grams of carbon-12. So this is the definitions of a mole. Okay, so first we need to understand how many atoms are there in 12 grams of carbon-12. Okay, so how many atoms are there in 12 grams of carbon-12? So this is the number. In 12 grams of carbon-12, we have this amount of carbon atoms, okay, which is known as the Avogadro constant. So 12 grams of carbon-12 contains 6.02 times 10 to the power of 23 carbon atoms. So this is the the fact that you need to know. And what is so special about this amount is this amount is simplified to 1 mole. It's simplified to 1 mole of carbon 12. 1 mole. So as long as you are having this 6.02 times 10 to the power 23, then it is equal to 1 mole. So that is the concept of 1 mole. 1 mole means 6.02 times 10 to the power of 23 of a particular substance. So 1 mole is equal to that. So remember, okay, 1 mole is 6.02 times 10 to the power of 23 particles. In general, I call it particles. The particles here can be atoms, can be ions, can be molecules, So in general, I call it particles. So 1 mole equal to this amount of particles. Okay. Now, a mole is the AR or MR expressed in gram. So example, 1 mole of carbon 12 is equal to 12 grams. So this concept of 1 mole is kind of important because you want to know the mass of 1 mole, then it is straight away equal to the relative atomic mass or the relative molecular mass. So for example, right, if I have 1 mole of carbon dioxide, then you look at the MR of carbon dioxide, which is 44, right? So 1 mole of carbon dioxide is actually 44 gram. 44 gram. So that's why it's kind of convenient to interrelate. Okay, the MR is 44. It means 1 mole of carbon dioxide is 44 gram. So let's say another example. If helium has AR of 4, that means, try to write. Yeah.
So the 44 gram is basically the RAM lah. The RMM.
Yeah.
Are you sure? Okay. So 6.02 exponent 23 is like basically to know how many atoms is in that mole of carbon dioxide.
Yes, correct.
Okay.
Okay. Okay, so let's continue my example here. If the AR is 4, right, that means 1 mole of helium is equal to 4 gram. So at the meantime, you have to know how many atoms are here. There are 6.02 times 10 to the power of 23 atoms of helium. Okay, so from here, we know in 1 mole of a substance, the mass, you refer to the AR or the MR. The number of atoms, you refer to the Avogadro Constant. Okay, so let's say another example. Let's say I use carbon dioxide again. Okay, I use carbon dioxide again. So if I have 1 mole of carbon dioxide, I know that this is equal to 44 gram of carbon dioxide. So this is what we know. And we also know that there are 6.02 times 10 to the power of 23 molecule. You see, now I use molecule because carbon dioxide is a molecule. Molecules of carbon dioxide. Okay, but be careful with this because these molecules of carbon dioxide contains of 1 carbon and 2 oxygen, which means there are 3 atoms here. There are 3 atoms here, so which is equal to 3 atoms. So one carbon dioxide molecule has 3 atoms. So because of that, if I want to find out how many atoms there are, so I have to take 3 multiply with 6.02 times 10 to the power of 23 atoms of carbon dioxide. Then how many atoms are here? So we can just press calculator to find out. So which is 3 times 6.02 times 10 to the power of 23. So we get 1.806 times 10 to the power of 24 atoms of carbon dioxide. So you see the situation here. 1 mole, 6.02 times 10 to the power of 23 of what? Of molecules. If this is molecule, then this is molecules here. But if this is atoms, as in here, helium is atom. If helium is atom, then 1 mole of helium has this amount of atoms. So you have to be careful with the words used here. So if this is atom, you use atoms. If carbon dioxide is molecule, then you use 6.02 times 10 to the power 23 of molecules. And if it's molecules, you want to find out the atoms inside, so you have to times. You have to figure out how many atoms in the molecule, then you multiply with that number. Okay, so let's say if I don't have 1 mole, I have 0.5 mole. 0.5 mole of carbon dioxide. So logically, everything is half. So it should be 22 grams of carbon dioxide. And how many molecules should be half of the Avogadro? So which is 3.01 times 10 to the power of 23. So where I divide by 2, the Avogadro constant, molecules of carbon dioxide. So how many atoms are there? Times 3. 9.03 times 10 to the power of 23 atoms of carbon dioxide. So that's how we interrelate between the mole, the mass, and the number of molecules, and hence number of atoms. Okay, so seems to be like many things here. So we can simplify it by using formula. You want to find out the number of moles conveniently. So the formula is take the mass divided by the molar mass. So the molar mass means the relative atomic mass or the relative molecular mass. So that's the molar mass.
So, can I know how did you get the number of atoms of carbon dioxide for 0.5 moles of carbon dioxide?
Yeah, how I do is I multiply with 3. Okay, I multiply with 3. I take this value, I multiply with 3. Why I multiply with 3? Because one carbon dioxide molecule contains 3 atoms. So that's why I multiply with 3.
Okay, sir.
Okay, so let's come back to this part. The convenient way to find out the number of moles is take the number of moles equal to mass over molar mass. So let's say, for example, how to use this formula. Okay, if I have 22 grams of carbon dioxide. Okay, so I want to find out the mole. How many mole? How many mole are here? Then I can use the formula given over here. So you want to find out the mole, the number of mole. So we take the mass, 22 grams, divide by the molar mass. The molar mass is calculated here. This is the molar mass, 44. 44. So 44 We substitute at the bottom. Okay, then we get 22 over 44. We get 0.5 mole. So which match with what we discussed just now? You see, 22 grams of carbon dioxide is 0.5 mole of carbon dioxide. So where we can find out the number of mole by taking the mass dividing by the relative molecular mass or molar mass. Okay, so that's why this is a convenient way. And of course, we can use this formula to find mass, for example, to find mass. So if you know the number of moles, then you can bring the molar mass to the left and multiply, and then you will get the mass. So let's say, for example, you want to find the mass. The formula is going to be like this. Rearrange the equation over there. Mass equal to the number of moles multiply with molar mass. Okay. Now, the number of moles, let's say I have 0.5 mole. The molar mass of carbon dioxide, let's say it is 44. Let's follow the MR of the carbon dioxide. So I multiply, I get 22. So which is same with what we discussed here. So if the mole is 0.5 mole, then the mass is 22 grams. So you can use formula to count it also. It's easier. Okay. Now, the other thing is, it is not written here, but we can easily figure out accordingly. Okay, so where if you know 1 mole contains 6.02 times 10 to the power of 23 particles, and then we can just create a formula which is similar to this. Okay, so something like this. If you want to find out the number of mole, you just take the, just now it's mass over molar mass. Okay, now you just need to take the number of particles divided by Avogadro constant. So this is a formula to find out the number of particles. Okay. So although it's not given here, but we can easily figure out in this way. So let's say, for example, right, if I have 3.01 times 10 to the power of 23 molecules of carbon dioxide. So example, I have 3.01 times 10 to the power of 23 of molecules of carbon dioxide. Then I want to find out the number of mole. So to find out the number of mole, so you just need to take the number of molecule, 3.01 times 10 to the power of 23, divided by Avogadro, 6.02 times 10 to the power of 23. Okay, when you divide, you will get 0.5 mole. So which match with the information that we discussed here. So this amount of molecules, you divide by Avogadro, then you get the number of mole, which is 0.5. So we have this now. Okay, then we have moles in gases. Okay, so there is another formula here where they give it in this way. Volume equal to number of mole times 24. So I prefer to put it in this way because our topic here is asking the mole. So mole is equal to the volume of gas divided by 24 dm3. So since the bottom is using dm3, right, the volume on top, we have to use dm3 also. if they give you cm cube, then you just need to divide by 1000 to change it to dm cube. Okay, so let's say example, how we use this formula for the mole of gas. Okay, so let's say I put the example on this side. Okay, carbon dioxide again. So let's say carbon dioxide occupied the volume of 500 cm cube. 500 cm cube. So I want to find out the number of mole in this 500 cm cube. So in order to do so, what am I going to do is, in order to find out the mole of carbon dioxide in this 500 cm cube, so I use the formula mole equal to volume over 24. This 24 is for room conditions. Room condition. Room condition means 25 degrees Celsius, pressure is 1 atm. So room conditions, we use 24. Okay, so there is another one which is not in the syllabus. So in the IGCSE chemistry, we just care about 24. Okay, 24 is for room conditions. Okay, now
so the 22.4 is not in IGCSE.
Yes, it's not in IGCSE syllabus. 2.4. Okay, so mole equal to volume. So volume you have to change to dm cube. So you divide by 1000. Divide by 1000 to change it to dm cube. So which is 0.5 dm cube. Now you take the 0.5 divide by 24. Okay, then I press calculator. 0.5 divided by 24. So I get 0.0208 mole. Mole. Okay. So mole. So this is the number of mole for a gas. So you take the volume, divide by 24, then you get the number of mole. So the conclusion is there are three formulas to find out the number of moles. Okay, there are three formulas. So the first formula is here. Number of moles equal to mass over molar mass. Second, number of moles equal to number of particles divided by 6.02 times 10 to the power 23. The third formula, number of moles equal to volume over 24. So they are all together three formula that involve mole. You will realize that to find mole, we always divide. So the first formula is here, 1. The second formula is here, 2. And the third formula is here. We always divide to get the number of mole. And what we divide is always some constant. Okay, so as you can see, for number 1, molar mass constant. Number 2, divide by 6.02 times 10 to the power 23. This is the Avogadro constant. It's a constant again. Formula number 3, we divide by 24. This is the volume in room, the volume of 1 mole in room condition, which is also a constant. So the bottom is always constant when you want to find mole. Okay, now let's move on. Okay, now we are here, concentration. Concentration is equal to number of moles divided by volume, but the volume is in dm cube. dm cube. So if they give you cm cube, you divide by 1000 to change it to dm cube. So let's say first point here, moles per dm cube. So this is the units of concentration. You see, this is mole, this is dm cube. So mole per dm cube is the unit. So mole per dm cube. You can also write capital M to represent mole per dm cube. We also have another unit to represent concentration, which is gram per dm cube. So gram per dm cube, that means on the numerator, you don't use number of moles anymore. You use the mass in grams, then divide by the volume in dm cube. And then you get your concentration as gram per dm cube. Okay, so let's say one example. Okay, one example, how we use the concentrations formula. Okay, so let's say I dissolve 22 gram of, let's say 22 gram of magnesium nitrate into water. I dissolve 22 gram of magnesium nitrate into water. Okay, then find the concentration in mole per dm cube. Okay, so first of all, when you see this question, right, you know concentration in mole per dm cube, the formula is number of mole divided by volume in dm cube. Okay, so let's say I add one more information. Dissolve 22 gram of magnesium nitrate into let's say 200 cm cube of water. Find the concentration in mole per dm cube. Okay, so our concentrations formula, yes?
First thing, we have to change 22 grams to mole first.
It's 22 grams. Okay, mole over volume. So you want to change the 22 gram to mole, then we have to use another formula, which is where I label number 1 just now. So you want to find the mole, then you have to take the mass divide by the molar mass. Molar mass. Okay, so we have to use this formula first. Okay. Now you want to find the molar mass. Molar mass means the AR or the MR. So for this case, this is a compound. So we call this MR. So you want to find the MR of magnesium nitrate. Okay, MR. MR means molar mass, basically. MR of magnesium nitrate. So we have to look at the periodic table. To find out the MR of magnesium nitrate. So I know that magnesium is 24. Then I know that nitrogen is 14. Oxygen is 16. 3 oxygen there, so 3 times 16. 3 times 16. And then the whole thing had to multiply with 2. Because of the 2 here, so that's why I need to multiply with 2. Okay, then I will get the MR. So I use calculator. 24 plus 14 plus 3 times 16, then times 2 again.
$148.
Okay, 148. So once we get 148, then we use this formula to find the mole. Mole equal to 22 grams the mass divided by the molar mass, which is 148. Okay, so 22 over 148. So we get a decimal number 0.14865. Let's say this is the mole. Then we can find the concentration by using the formula. Okay, now we continue here. The concentration is equal to the mole, 0.14865, divided by the volume in dm cube. So you change this to dm cube, divide by 1000. then you get 0.2 dm cubed. So we have to divide by the volume, 0.2. Okay, so divide by 0.2. And then we get the concentration, which is 0.743 mole per dm cube. So that is how we use the concentration formula. Okay, now let's continue. Okay, so on the first page, we have one more subtopic, which is here, molecular formula. Molecular formulae, the formula using the actual number of atoms in a molecule. So what is that? So example, carbon dioxide is a molecular formula. Sulfur trioxide, molecular formula. H2O, molecular formula. So molecular formula is the formula of a molecule. From here, you can also see the actual number of atoms in the molecule. For example, H2O contains 2 hydrogen and 1 oxygen. You can see that from the molecular formula. You can see how many atoms of each type in the molecule. Okay, so that is a molecular formula. Compare with empirical formula. Empirical formula is the simplified version of the molecular formula. So this is the simplest ratio of the atoms in a compound. Okay, so for example, let's say if I have glucose, C6H12O6. This is actually the actual formula, which is known as molecular formula. Molecular formula. Now you can simplify the 6 to the simplest ratio, which is 1 to 1. So if you do so, 1 to 1, for 1 we no need to write down. So that's why we end up with CH2O. So this is the simplified version. We call this empirical formula. Okay, so another example, let's say you have, let's say butane. So butane, the formula is C4H10. So this C4H10 is the actual formula, which is the molecular formula. Now we can simplify this. 4 and 10 can simplify to the ratio of 2 and 5. Divide by 2 for both numbers. So C2H5 is actually the empirical formula. Empirical formula. So sometimes the molecular formula and empirical formula looks the same. So for example, let's say water. Water H2O. H2O is the molecular formula. And if you go and simplify it, it's still 2 to 1. So that means the empirical formula is also H2O. So we have to know that. Okay. Now, let's see the example here. The second point. For example, molecular formula of ethanol, C2H5OH. Empirical formula of ethanol, C2H6O. So you will realize they don't simplify it to a smaller number. They are just combining only, 5 hydrogen plus 1 hydrogen becomes 6 hydrogen, and then combining. So this is the same with this. They don't simplify the numbers. Cannot simplify basically, because this 261. 261 you cannot divide by any common numbers anymore. So cannot simplify. So that's why in this case, molecular formula is equal to the empirical formula. Okay. Now to find out the empirical formula, you have to make the percent ratio into the simplest whole number ratio. And note, if given percentage, use them as grams. Okay, so for example, something like this. Okay, so they give you the percentage of element X and element Y. So you have to take the percentage as mass straight away.
Yes, I understand.
Okay, so have the mass, then you divide by the molar mass to find the mole. Okay, then you have to put them in the simplest ratio, and that ratio will help us to get the empirical formula. Okay, so that is why we built this table. We built this table to find the empirical formula. Okay, now here, divide the coefficient of each element symbol by the lowest coefficient. So we have to, you want to put them in ratio, right? So you have to look at the number of mole of these two. Whoever's smaller, you divide by that numbers, and then you get in ratio. Okay, so we will practice this later on this part. Let's move on first. Percentage purity. Okay, so formula, mass of the product which is pure over mass of the compound which is impure, multiply with 100. Percentage purity. Okay, so this is the formula, pure over impure times 100. Okay, so for example, right, you want to find out how pure is the gold. So we find out the mass of gold in let's say in the ring. Okay, we find out the mass of gold in the ring. Divide by the mass of the whole ring. We have to know that in the ring, not 100% of the ring are made of gold. They should have some impurity. So mass of the ring
So
itself.
can you please repeat it?
Okay.
I still don't understand.
Okay. So let's say you have a ring. The ring is, let's say, 50 gram. 50 gram. You don't expect this gold ring is made of 50 gram of gold, 100% made of gold. It's not. Okay, so let's say the ring is 50 gram, but the gold inside is just, let's say, the gold in the ring is just 45 gram. There are 5 gram of impurities. So 5 gram of impurity. So let's say something like this. The ring is made of gold with some impurities. Okay, now you want to find the percentage of purity. The percentage of purity. So we take the mass of the product, the mass of the gold, which is 45, over the mass of the compound, 50 gram, total mass basically. 50, then times 100, then you get 90%. So that means the ring is made of 90% of gold. Okay, so that is an example. Now, percentage yield. Percentage yield, the formula is actual mass obtained divided by calculated mass multiply with 100. Okay, so of course I have to explain it in this way. Actual mass obtained is the mass obtained from experiment. from experiment. Calculated mass is through calculation. Through what kind of calculation? Through, for example, we look at the chemical equation and we calculate the mass accordingly based on the ratio. So calculated mass at the bottom is theoretical value. In practical, sometimes we can't get one. So that's why we take the actual mass from experiments, divide by the calculated mass from theory, multiply with 100, and then you get the percentage yield. So let's see one example. Okay, so example for this. Okay, let's say when calcium carbonate of 200 gram is heated strongly. Okay, then we have 120 gram of calcium oxide is formed. Find its percentage yield. Okay, so what we are doing here is we heat up the calcium carbonate. We heat up 200 gram of calcium carbonate. We heat it up, then after a while, we cool down the calcium carbonate. We cool down the residue, the remaining part, and we get 120 gram. So the 120 gram is calcium oxide. Calcium carbonate, after you heat it, it becomes calcium oxide. Okay, so find its percentage yield. How to find? So the formula is actual mass obtained over calculated mass. So we have actual mass actually. Actual mass obtained. Okay, so actual mass obtained is, I write down first. Actual mass obtained is 120 gram of calcium oxide. This is the actual mass obtained. Calculated mass. So calculated mass. Let's see how we do it. Calculated mass. You want to find out the calculated mass, you need to first write the chemical equation. Calcium carbonate. You heat it strongly, it becomes calcium oxide plus carbon dioxide. Okay, so is the equation balanced or not? You see calcium, one calcium on the left, one calcium on the right, balance. One carbon on the left, one carbon on the right, balance. 3 oxygen on the left, oxygen 1 plus 2, 3 oxygen on the right. So it's already balanced. So this is the chemical equation based on what we learned from the theory. So where we know heating carbonates, you get oxide and carbon dioxide. Yeah? So that's what we learned, and we just write down and do calculation. Okay, now we are using 200 gram. So 200 gram divide by, I'm going to find out the mole of calcium carbonate. Okay, so calcium, let me check the Let me check the periodic table. Periodic table. IGCSE chemistry periodic table. Image. Oh, this one that give proton number only. Okay, let me find another one. This should not be, because this is too many decimal. Okay, let's see this. IAL is at Excel syllabus. Okay, let me see. Cambridge. Okay, so from the periodic table, we know that calcium takes 40 as the RAM. You can see it from here, calcium. Okay, so let's continue. Okay, so calcium, the relative atomic mass is 40. Carbon, I know already, is 12. Oxygen is 16. So 3 oxygen there, 3 times 16. Okay, so I find out the mole first. So 200 divided by 40 plus 12 plus 3 times 16. Okay, so what I get is 2. I get 2 grams. Yeah, 2 mole. Yeah, any questions?
No, I was just calculating stuff.
Oh, so I get 2 mole. So if you have the mole, so actually you can just use ratio. What kind of ratio am I saying? You look at the number in front, right? This is 1 calcium carbonate to 1 calcium oxide and 1 carbon dioxide. So the ratio is 1, 1. Okay, 1 to 1, same that means. So in other words, if we get 2 mole for calcium carbonate, we should expect to get 2 mole calcium oxide. Of course, we also get 2 mole of carbon dioxide because the ratio is 1, 1, 1. And that means if this is 2 mole, this will be 2 mole. Carbon dioxide also 2 mole. But we don't want to care about carbon dioxide here. Okay, so we just care about calcium oxide because our concern is calcium oxides, the calculated mass for calcium oxides. So we have the mole of calcium oxide now. Now I want to find the mass.
Sir, can you repeat how you get 2 moles for calcium oxide?
Okay. The way to get 2 mole of calcium oxide is by using ratio. You see the ratio here is 1 to 1. 1 to 1 means same.
Okay, sir. Understand.
Right. Let's continue. Mass equal to mole. Once I get the mole of calcium oxide, right? So I want to find the mass of calcium oxide. So I take mole, multiply with molar mass. of calcium oxides. So the mole is 2 mole. The molar mass for calcium oxide is easier to count. It's just 1 calcium, 40, and 1 oxygen, which is 16. Okay, then we just press calculator. 2 times 40 plus 16.
It's 112.
112. Okay. 112 gram. 112 gram. Huh? Okay. Calculated mass. Okay. Now I need to change the values that I set here. Okay. So because calculated mass must be greater than the experimental value. So this one I need to change it. I cannot, just not as simply put one. I cannot use 120 gram anymore. Let's say I just obtain 100 gram of calcium oxide through experiments. So actual mass obtained is 100 gram. From experiment we get 100 gram, but when you do calculation based on theory, you get 112 gram. So calculated mass is 112 gram. So in that case, you want to find the percentage. You see the formula again. Percentage U, actual mass obtained over calculated mass. Okay, so you want to find percentage U. That's going to actual mass, 100 gram. Calculated mass, 112. Multiply with 100. Okay, then you get 100 over 112 times 100. Then you get 98.3%. So something like this. This is how we do the percentage yield. Okay, experimental value divided by theoretical value times 100. Okay, now the last part. So now we have a practice to write down the formula of the ionic compound. Okay, so we start with potassium chloride. So you have to know that potassium is K. You have to know its charge also. Chloride is Cl.
KCl.
KCl. So the charge balance of KCl. Yeah. Copper 1 oxides.
That is CuO. Yeah. 2 copper is 2 positive.
2 negative. So imagine.
Copper is 2 positive, right, sir? Cu2 plus.
It's copper 1. So that's why Cu positive.
Okay.
So look at the Roman numeral in brackets. So
okay.
It's 1 oxide, 2, so we exchange. Cu2.
Cu2. Oh.
Yeah. Cu2. Lead 2 bromide. Yeah.
Fe2
plus.
Oh.
Lead.
And
bromide.
Br negative.
Negative. So 2, 1, exchange. So Pb take 1, Br take 2. So Pb, Br, 2. Iron 3 chloride. Okay, so
Fe3 plus and Cl negative.
Yeah, Fe3 plus. 3 and 1, exchange. So Fe 3. Okay, so FeCl3. Magnesium sulfate. Okay.
Mg2 plus
P2 plus.
and SO42 negative.
Yeah. So if you have 2, right, you simplify it.
Okay.
It's possible to simplify. You simplify it to 1, then only you exchange. So it's 1, 1. So magnesium take 1, sulfate also take 1. Then we have zinc chloride.
Zinc 2 plus and Cl negative.
So we look at the number only. 2, 1, exchange. Okay, so zinc take 1, Cl take 2. So zinc, Cl, 2. Okay, aluminum chloride.
Al3 plus and Cl negative.
Yeah, Cl negative. 3 and 1, exchange. So we get Al, Cl, 3. Potassium nitrate. So potassium is K plus.
K positive, NO2 negative.
And 3.
Oh.
And 3. NO2 is nitrite. 3 is nitrate. And
Okay. So I can't hear you.
Yeah, KNO3. Yeah. Then calcium hydroxide.
Calcium is Ca2 plus
2 plus.
and
Hydroxide
OH negative.
2.
Ca1 bracket OH2.
Yeah, Ca and H2. So we have to put bracket when there are more than 1 and in the ions here. More than 1 element. More than 1 element, and it takes multiples ions, and then you put bracket. Ammonium sulfate. Ammonium is
NH3, NH4,
NH4.
4 plus, and SO42 negative.
Okay. Exchange the charge. 1 and 2. Okay.
The
So
NH4 has to be in the bracket.
Because 2 elements.
Yeah.
And they take multiples ions. Sulfate. Silver chloride. So
Ag plus and Cl negative. So
yeah.
it's just one AgCl.
Calcium chloride.
Ca2 plus and Cl negative.
2, 1. Exchange.
Yeah.
So Ca, Cl2. And then iron 2 hydroxide. So iron is Fe plus hydroxide OH minus. 2, 1. Exchange. Fe OH 2. Calcium carbonate. Ca 2 plus. Carbonate CO3 2 minus. This is 2. Again, you can simplify it to 1, 1. Exchange. So you get calcium carbonate. Lead 2 sulfate. Pb 2 plus. Sulfate SO4 2 minus is 2, 2. Again, you simplify it to 1, 1. Exchange. So Pb SO4. Chromium 3 Cr3 plus. Sulfate SO4 2 minus. And this is 3 and 2. Exchange. So chromium now take 2. Sulfate more than 1 element. Bracket it and take 3. Lead 2 Pb 2 plus. Nitrate NO3 minus 2 and 1 exchange. So Pb bracket, because nitrate has 2 elements, NO3 times 2. Sodium chloride Na plus Cl minus 1 1. So NaCl. Magnesium oxide Mg2 plus.
It's just MgO.
2 simplify to 1 1. MgO. Then lead 2 oxide Pb2 plus, oxide 2 minus is 2 2. Simplify it to 1 1. So we have PbO. Sodium sulfate. This is 1 2 exchange. So sodium take 2 and Na2. Sulfate take 1. Copper hydroxide 2 1 exchange. So we have CuOH2. Okay, so I think should be enough for now. We have done the theory for this chapter 2 already. Chapter 4.
Okay, sir.
Okay.